Yeah, so I'm going to talk about the strong CP problem, the Swampland. Let me first just remind you about the strong CP problem. The strong CP problem is the problem that we have this potential term in the standard model, the theta term coupled to gluons, the CP odd term. And we don't see it in the real world around us. We measure the neutron EDM, or we fail to measure a non-zero neutron EDM. And as a result, we can conclude that this theta angle is smaller than 10 to the minus 10, and we don't know why. And there are two basic paradigms when people have thought about models to solve this problem. And I'm going to say a couple of things in this talk about each of them. The first is the idea that there's something special about CP, that even though we see CKM, we see a CKM phase. So we know that CP is violated in the world around us. That's an order 1 phase. Maybe CP fundamentally is a symmetry of nature and it's just spontaneously broken. It's spontaneously broken in some way that if you're clever enough, you could imagine a model that generates the CKM phase but does not generate theta. And it's not easy to do that. It's hard to build a model that works without some effect that feeds into theta. But there are clever enough people, and Nelson wrote such a paper when she was a grad student, and these are now called Nelson bar models. So that's one option. The other option is that CP is simply not a symmetry of nature in any sense whatsoever. We should generically expect all CP phases to be order 1, and it's something really special about theta that it becomes small because of some dynamics, like a dynamical axion that can relax and make this coefficient 0. Now, I think the strong CP problem is a great test case for swampland ideas because, first of all, it's an important problem. It drives a lot of thinking and phenomenology, and in particular, it gives us a very nice model of dark matter, which is the axion. So it's important, but it's also closely tied to symmetries. And we know that we should have doubts about global symmetries or approximate global symmetries in theories of quantum gravity, and that's why this is a good case for bringing in swampland thinking. And the first class of solutions I mentioned, the parity solutions like Nelson bar, and those CP itself is a symmetry, and we should ask, what does it really mean? In particular, it's a symmetry that's spontaneously broken. What happens to the domain walls? That's going to be the first part of my talk. And then the axion solution, what we need is that the continuous shift symmetry of the axion is explicitly broken by this coupling to gluons, but that is by far the leading source of breaking of the symmetry. Anything else that broke the symmetry would generically introduce a different phase that would become a strong CP angle that we don't see. And the absence of those other terms is what's frequently called the axion quality problem. Okay, so both of these are problems that we should think about in terms of their symmetry structure and ask which of these solutions is compatible with what we know about quantum gravity. So I'm going to start out talking about the first kind where we imagine that CP is an exact symmetry of nature. This is work that I'm doing with Jake McNamara. And the basic question here is about domain walls. So if CP is a symmetry, if it's an exact symmetry of nature, it's spontaneously broken, then when it was broken in the early universe, domain walls would have been formed. And stable domain walls are a cosmological disaster. They redshift more slowly than matter or radiation. They dominate the energy density of the universe, and they don't lead to the hot Big Bang cosmology that we see experimental evidence of. Now, one way out of this is to say maybe it's not an exact symmetry, but it's an approximate symmetry that's explicitly broken. And in fact, there's a lot of literature on this. If you go looking at the phenomenological literature on these spontaneous CP breaking models, what a lot of people say is, well, gravity breaks symmetries, so let's write down a theory that has CP symmetry and then add some irrelevant Planck suppressed operators that break it. And I think that's complete nonsense. We don't take quantum field theories and tack on gravity as sort of an afterthought that gives us Planck suppressed operators. We have to have a coherent picture of quantum gravity as kind of a holistic theory that includes the particle physics we want to see. And if something is simply not a symmetry, if it's explicitly broken, there's no reason not to add every term that violates the symmetry, including all the relevant operators, and those would totally ruin any of these models. Okay, so there's just kind of a basic philosophical problem with the way that I think people have been thinking about these models. And the right way to think about it is if you want CP to be a symmetry that's spontaneously broken, you should start with CP actually being a symmetry. And it's a symmetry of spacetime, it should be some exact gauge symmetry of spacetime. Now, before I talk about CP, let me remind you about just general discrete symmetries or finite group symmetries that are internal symmetries. Okay, so these are not spacetime symmetries. These are things like, say, a Zn symmetry that gives us a Zn phase for some scalar fields. Any theory that has such a symmetry has a Lagrangian that's invariant under the symmetry, and you could ask, how do we know if it's global or gauge? Okay, with continuous symmetries, it's easy because when you have a gauge symmetry, you have a gauge boson that's an actual propagating mode. But if I have a symmetry like Zn, I don't have a propagating ZN gauge boson. But there is a lot of physics that knows the difference between global and gauge. And one piece of physics that knows the difference is the existence of some kind of object, which is a codimension 2 dynamical object that I'll call a twist string or a twist vortex. This is something that if I take a particle that has charge and I move it around the string, it picks up an Aharonov-Bohm phase. Or in other words, it comes back to itself only up to a gauge transformation. The most familiar case are the Krausable-Check strings of ZN gauge theory, but there's such a thing for any finite group gauge theory, or more generally, anytime you have kind of disconnected components of your gauge group, there will be objects like this. And some of us argued in a paper last year, I think all the authors of the paper are participants in this workshop. We argued that these twist vortices actually have to exist as dynamical objects in quantum gravity to avoid a generalized global symmetry that would arise if they did not. So there's a two-form symmetry generated by Wilson line operators, which is explicitly broken by the existence of such strings. Okay, why am I talking about these strings? It's because they play a big role in the physics of domain walls. So let's imagine that I have, say, a theory with a Z2 internal symmetry. It has some potential like this. It has two degenerate minima at phi equals V and minus V. Of course, they're not really different physical states because they're related to each other by gauge invariance. But still, in the limit where you think of this as being basically like a global symmetry, when you spontaneously break the symmetry, you can get a domain wall that separates the plus V vacuum from the minus V vacuum. There's some finite tension object here, which is interpolating between these. And those would form during a phase transition in the early universe through the Kibble-Zurich mechanism. And they would be a cosmological disaster if they were stable. But they don't have to be stable for these internal discrete gauge symmetries. It's possible to cut a hole into a domain wall using these cosmic strings, the twist vortices that I mentioned before. So you can imagine this twist vortex, which when you circle around it implements the gauge transformation, allows you to connect the plus V over here with the minus V over there. And you can nucleate such a vortex in your domain wall. It will expand and eat up the domain wall and destroy it. Okay, so at least in principle, these are unstable. In practice, you have to ask how quickly this happens in the early universe and whether there's still a cosmological problem. But this at least makes it okay to imagine finite group gauge symmetries that are spontaneously broken in the early universe without domain wall problems. And we can ask, does CP work in the same way? Do CP domain walls have this property? And the answer is no. So that's our result. CP, counter to some claims people have made in papers, CP cannot have such a string. So CP domain walls are exactly stable, and this is just a mathematical fact. It's a consequence of topology. So to explain that, I should tell you how to think about a theory with CP, or more generally with parity or any kind of orientation reversing spacetime symmetry. This, I think, has confused people because if you open up, say, Peskin and Schroeder's quantum field theory textbook or something like that, you will be told that parity is an operation that sends a point x in space to a point minus x. So it's mapping one point to another point. And that's fine if you're in Minkowski space, but it's not clear what it means if you're in a general curve spacetime. If I hand you a point x on some manifold, you can't tell me what minus x is. So we need a better way to think of these symmetries. And there is a well-known better way, at least well-known in the formal field theory community, not so well-known to particle phenomenologists, which is that a theory with a symmetry like parity is a theory that you can define on a non-orientable manifold. So a theory like the standard model cannot be defined on such a space. Imagine if I tried to define the standard model on something like a Klein bottle, I could take my left-handed neutrino, which exists in the standard model, and I could move it around some cycle, and it would come back, and it would have to be a right-handed particle when it came back because the orientation flipped when I moved around. But there is no right-handed neutrino in the standard model, so that doesn't work. So the only theories that you can define on non-orientable manifolds are theories that have this kind of structure, this orientation reversing symmetry structure, and that's what we'll take to be our definition of a field theory with parity. Or we could generalize this to CP if we're also conjugating fields when we move them around. And as far as I can tell, nobody has really worked out what this means for phenomenology and cosmology. So that's what I want to tell you. So as an example, let's talk about a Mobius strip. Hopefully you've all at some point in your life actually played with a Mobius strip. Take a strip of paper, twist the end, glue it back together, and see what happens. This is a non-orientable manifold, meaning if I try to pick coordinate charts to cover my manifold, say I want to cover it all with right-handed coordinate charts, at some point, I will find that I can't do it because this edge is glued to that edge with a twist. The white point is glued to the white point. The black point is glued to the black point. So if I'm right-handed here, when I glue here, this becomes left-handed. And so in moving from this coordinate chart to that one, I have to flip my orientation from left-handed to right-handed. And we can define fields like pseudoscalars in a theory with parity on such a manifold as fields where the value that you would have on this coordinate chart where you picked right-handed and the value I would have on that coordinate chart where I picked left-handed only agree with each other up to a minus sign. So in this overlap, we have to add an extra sign, or in the case of CP, an extra complex conjugation. And now we can ask, what would it look like to spontaneously break parity on a manifold like a Mobius strip? Okay, so imagine I have this potential. I want to write down a vacuum field configuration. So I start with a field that's plus V. I move to here, it's plus V. I move to here, it's plus V. I move to here, and I've now crossed into a coordinate chart with a different orientation. So I better pick minus V. But this minus V doesn't agree with the plus V there. The minus V here glues up here. And so I need something in between to interpolate between plus and minus. Okay, so you can play with this, try different ways of writing down field configurations. You will find that you cannot do it without a domain wall. The domain wall interpolates between the two minima, and it allows you to write down a parity violating field configuration on the non-orientable manifold. This domain wall wraps what's called the, it wraps the cycle corresponding to the first Whitney class. And if you cut along that, you get something oriented. Maybe you've also done that with an actual Mobius strip, cut it with scissors down the middle, it becomes oriented again. So this is fun. You can play with Mobius strips and figure things out about the physics. In particular, this domain wall has to exist, and we can't destroy it. If there was a local process, like the one that tore a hole in the domain wall with the cosmic string, in this lower number of dimensions, that would just look like tearing a hole here with two things on the end. But then we could go through the hole and connect these two sides that aren't supposed to be connected. If we could do that, we could define an orientation on the manifold, but the manifold is not orientable, so that's mathematically impossible. Okay, so we have drawn the conclusion about physics that there is no local process that tears a little hole in the domain wall. And that conclusion, because it's a local conclusion, applies whether I'm talking about physics on this crazy space or physics just in ordinary flat space. Okay, so these domain walls have to be absolutely stable. It's just a topological requirement. And that's important for the cosmology, because if we have a CP violating phase transition, we make domain walls. And the only way I know of to get rid of them is to inflate them away. If the phase transition happens early enough, and inflation is still going on at or after that time, then inflation can just take the domain walls and spread them very far apart from each other so that they don't have it. But that's a really important thing for the physics, because to take the original Nelson bar model, for example, it needs the CP violating scale to be below 10 to the 8 GeV. If you try to push it higher, you find that you somehow regenerate a theta term through RG effects. So what we know from data is the Hubble scale during inflation was below a few times 10 to the 13 GeV. But in a model like this, you would need it to be many orders of magnitude smaller than that. And that's a big deal. We're thinking about models of inflation and how we observe evidence of them. Now you can try to get around this, and here's sort of a challenge to model builders. You can imagine building a model where you violate CP at much higher energy, but you do it in a hidden sector that doesn't communicate with the standard model, except through some very weak interactions. So some kind of sequestered hidden sector. The domain walls are stable, they get inflated away, but maybe inflation still happened at a high scale. And then below that, you still have the standard model with what looks like some small explicit CP breaking that came from its weak interactions with the sequestered sector. And then you're kind of back in something kind of like the scenario that people have studied a lot. You can again have a phase transition where a pseudoscalar that talks to the standard model gets about. But now the domain walls are unstable because of the explicit breaking that they get by communicating with this other source of CP violation. And that's potentially a good cosmology. It won't look like just Planck suppressed operators. It'll be some other kind of weak interactions. And so that's part of the challenge, is figure out what version of this model actually makes sense. And in particular, there's a possible tension between turning on enough CP violation that you make these domain walls decay fast enough, but not enough CP violation that you spoil the thing you wanted to do in your model to begin with. But if there is such a model that can solve those tensions, it might predict interesting gravitational wave signals from this relatively low scale phase transition, which would make domain walls that would then disappear. So we have not thought about these model building details so far. We've only thought about kind of the generic topological facts. But I think this is an interesting challenge that will give people a new perspective on some of these models that have been floating around for a few decades, but that are kind of not resting on a firm foundation at the moment. Okay, that was part one of the talk. Part two, I want to say a few words about axions as gauge fields. I'll say a little bit more about this actually tomorrow, also when I give a colloquium. This is partly based on the paper that I wrote with Ben, Jake, Miguel, Tom, and Irene on Chern-Vase symmetries back at the end of 2020. So a question that I think is important to understand is that we find axions all over the place in string compactifications. People who build models of particle physics and string theory find lots of axions. And you can ask why. Is it a lamppost effect that we're looking at certain highly supersymmetric vacua and they happen to have these moduli in them? Or is there a deeper reason? And what we want to suggest is that there's a deeper reason. And the basic argument is, if I look at a Lagrangian for an axion field theta that's coupled to some kind of instanton number density for some gauge field, my equation of motion tells me this instant density looks like a derivative of the axion shift symmetry current. And if I integrate both sides of that equation, I get that the total instanton number density on spacetime is 0, because it's the integral of the total. So this looks like a Gauss's law. This looks like we gauged something. It looks like we gauged some kind of symmetry that counts instanton number. And that's the basic suggestion, is that quantum gravity doesn't like global symmetries. One global symmetry is the one that counts instanton number. And one way to get rid of that symmetry is to gauge it. And that's why we find axions all over the place, because they're gauging that symmetry. Now, there's something a little uncomfortable about that argument, which is that if I'm in more than 4 dimensions, then this current F wedge F does generate an honest symmetry. In 5 dimensions, instantons are particles. You can count them. It's a perfectly ordinary 0 form global symmetry. In 4 dimensions, this would be a -1 form U1 global symmetry, meaning it counts things over all of space-time, not over space or over lower codimension things. And -1 form symmetries are not quite as well defined as higher form symmetries. So I can't give you a super sharp argument that quantum gravity doesn't like these things. It is related to various conjectures. You could take a general enough version of the cobordism conjecture, for instance, that talks about cobordisms involving the gauge bundles on spacetime and try to make an argument there. But it's somehow different in character from the arguments that we understand really well. Nonetheless, I think there's something to it. I think quantum gravity really doesn't like these -1 form symmetries, and axions are doing the job of getting rid of them. And in fact, axions often come from higher dimensional gauge fields integrated over some cycle. So they really are coming from a gauge field that's gauging a symmetry. And the axion coupling to gauge fields comes from higher dimensional Chern-Simons terms in lots of the examples we know. Okay, so I want to say just a few more words about this. How much more time do I have? 5 minutes, okay. This fact that string theory has axions in it is not new. People pointed it out already in the mid-80s. And even in the phenomenology context, there's this famous paper called the string axiverse that came out, I don't know, 10 years ago or something like that. So people are familiar with the idea that string theory and quantum gravity might like axions. But I think there are differences, qualitative differences between the axions that people talk about in 4D models and the axions that come out of string theory or out of our expectations about quantum gravity that I think are not well studied enough and not talked about enough. So I just want to briefly say some things about that. If I have a conventional axion model, like the KSVZ model in 4 dimensions, I have some U1 global symmetry. It's not really a global symmetry because it's anomalous, but it's an approximate global symmetry. And it's spontaneously broken when some complex scalar field gets a bev. And in that theory, you can find solitonic solutions that are cosmic strings that the axion winds around. And these strings could form in cosmology. Again, there's some Kibble-Zurich mechanism that generically forms topological defects during phase transitions, would form a lot of these strings. They can affect the abundance of axion dark matter. People study this a lot. And in such a model, if you could measure F, which we could do if we discover an axion and measure its coupling to photons or gluons, what you would learn is the scale where this happens which is a conventional 4D scale where some symmetry broke. If f is 10 to the 12 GeV, you would say, well, physics is still 4-dimensional up to 10 to the 12 GeV, and that's interesting. And that's kind of what everyone has been studying in the context of axion physics. But when you look at the axions that come from string theory, they're not like this. The axion strings that we find there are actually fundamental strings. When I say fundamental, I don't really mean just F strings, but they're things like F strings or like D branes wrapped on some cycles. They're fundamental objects that know about UV physics. I can't just go to the core of the string and find some classical solution where F goes to 0. It doesn't work that way. F goes to 0 is not a finite distance limit in field space. And in particular, the scale F is usually related to fundamental scales. So usually in the context of these kinds of models, if I told you that we measured F to be 10 to the 12 GeV, you would not conclude physics is still 4-dimensional there. You would conclude that now we're getting to the scale where some stringy physics is coming in. And we probably have some large internal dimensions and a low UV cutoff. Okay, so qualitatively, the way you would interpret an experimental discovery is very different in these kinds of scenarios. And we should think about how to home in on that and whether there are experimental observations that would tell us which of these two classes of things is what we're seeing. Just in the last minute or two, I want to just briefly mention that I think there are things that we maybe still haven't explored enough where we can make parametric statements about how different scales are related. And I can make arguments from a few different points of view, the weak gravity conjecture, the Swampland distance conjecture, or the scalar WGC. But for now, let me just say something about a specific string construction, which is that if I build the standard model in type 2B on D7 branes, my axions come from C4. The volume of the 4 cycle where I put the standard model fields determines the standard model gauge couplings, 8 pi squared over G squared. You can ask, well, what are the axion strings? Well, there are D3 branes that I could wrap on the 2 cycle that intersects this 4 cycle. That would be something that the axion would wind around. And there's a relationship between 2 cycle volumes and 4 cycle volumes that you can just derive from the cubic relationship between the volume and the 2 cycle volumes. And if I just look at what these things mean in the axion context, this is related to the tension of the axion string. The second derivative of the Kähler potential is related to the decay constant, which we could actually measure. And the 4 cycle volume is related to gauge couplings, which again, we have measured. All this in string units, where the other factors here are just something of order 1. Okay, so this is just a statement about a specific class of models, but in fact, I can make similar arguments from other viewpoints, and I won't do that today. But I think there are reasons to think that some of these things might be rather general. So what you would conclude from this is that the string tension is proportional to the decay constant squared. That's kind of what you expect in generic 4D models. But here the proportionality constant is related to the gauge coupling, something like 8 pi squared over G squared. Such axion strings would obey the magnetic axion weak gravity conjecture, which says their tension should be less than F times m Planck, provided that F is smaller than G squared over 8 pi squared times m Planck, which is actually the electric axion weak gravity conjecture, if we plug in the instanton action for the gauge theory. And so in this context, we would conclude that actually, if we don't saturate the electric axion WGC, then we expect the magnetic axion WGC to also not be saturated and to have some room to spare. And if we measure a small f, this could be what's going on, and it would suggest that the tension of these strings is not far above f. And that's interesting, because these strings are fundamental objects. That means local QFT is breaking down at a low scale. And so if an experimentalist comes to us and says f is 10 to the 11 GeV, that's something to get kind of excited about, because that means in the context of at least models like this, we can expect the quantum gravity scale to be low. Now, of course, I'm plugging in a single axion here. There are mixing effects. There's a lot of other things to worry about. So I'm oversimplifying a bit, but I think this is the kind of thing we should be thinking about. And just to conclude, there's a kind of a big difference between conventional 4D axion theories and the ones that come from higher dimensional gauge fields. The way we interpret data would be very different. And I think people have not really been emphasizing this, even when people talk about the string theory axiverse in discussions of phenomenology. So just to leave you with the couple of words about the final conclusion, the Nelson bar type models have a serious problem in the stable domain walls, but there's also an opportunity to maybe build models that somehow get around that might be predictive. Axions, on the other hand, I think just seem to be what quantum gravity really wants to do. but I'm not sure that we fully processed how we would interpret a discovery of one in the context of quantum gravity. Thanks.
Any question? Yeah, Miguel.
That's super nice. Doc, I wanted to ask about the first part. Have you thought about couplings with the word volume theory of the CP domain wall, or what are the couplings to standard model fields? Is there anything universal one might say there?
Is there anything universal you could say about the domain wall, the effective theory on the domain wall?
Yeah, does it have like the dione collected coordinate on a monopole, something that you can figure out from anomalies, or from inflow from the standard model bulk, or some couplings? Or
that's a really interesting question. I don't immediately have an answer. There are examples of field theories where we know that there are mixed anomalies between time reversal and other kinds of symmetries, which suggests that there might be something interesting like that. But yeah, I don't have a clear answer for you.
Thanks.
Any other question? Yes, Ananda.
Very nice talk. I really enjoyed it.
Thank you.
Just a simple question. In the exercise you did for the design brain case, did you do it for D3s to see what comes out?
I have not. I don't think I've thought that through for D3s. I mean, I guess what you would expect for D3s would be,
because the gauge coupling is the string coupling.
the gauge coupling is determined by the dilaton, and the strings are like D7s that wrap the whole internal volume. So is it obvious? I think I would have to think more about where various factors show up. But yeah, we would somehow well, I guess what we would expect is the tension would be large because it's proportional to the internal volume. That volume factor also determines m Planck squared over m string squared. Sorry, I don't think I'm going to be able to think this through on the spot.
Yeah, don't worry, don't worry. We can speak
It's a good
later.
question.
I think it's very interesting. Very nice. Thank you.
Okay, I see no other question. Is there an online question? Okay, if not, thanks again for the nice talk.